Hello, and welcome to this introductory video on the Doppler effect. In this video, we're going to introduce the Doppler effect and a little bit of the maths to explain what's going on, but more fundamentally, we're also going to look at very conceptual ways of making sense out of why we get the equations that we get. So, in order to really sort of set the stage, let's first think about the fact that me, for instance, standing here talking, I'm emitting sound waves. Those things are pretty much moving in all directions, maybe not so much behind me, but they're coming out sort of in all directions, and if I maybe am like shouting towards the ceiling, then they would go in all directions around the room, at least horizontally. So if I'm emitting sounds in all directions, then that might look something like this. So I've got a little sound wave emitted, and then the next one, and then the next one, and they all are moving away from me as the source of that. Now in this animation, we've sort of chopped up time into sort of two stages. So there's one stage where everything moves, and then there's one stage where I emit the next circle. So you can see as we start again, I will emit that circle, I'll let it move, I'll emit the next one and move them both, emit the third, move all three, and so on. Okay, so we've just broken it up so it's a bit easier to see, just moving in discrete time steps in that sort of fashion. So this is sort of the nice thing. Each of these circles then, for instance, will represent, say, the peak of one of those sound waves. So I've got a nice uniform distance from peak to peak, which means I've got the same wavelength clearly in all directions, which makes sense. It's the same thing being emitted by that source. So how does this change then? What is this Doppler effect? And that's what the Doppler effect talks about. It talks about changes to this setup. All right. So here now, let's think about an observer who's actually going to make measurements of that sound. He's going to, or he or she is going to measure that wavelength, maybe the frequency, in fact. So as we're just sitting here, in each time interval, you see that the next wave front, or the next wave peak, reaches me in every single time interval. So here I'm going to start. This outer circle is about to reach me. So now we've detected it. Then we detect the next one in the next interval, and we detect the next one now, and so on and so forth. So every single time interval, I detect one wave if I'm just sitting here and letting the waves reach me. Okay, but what happens if the observer is actually moving? So instead of standing still, I'm going to go ahead and move towards it. So this is a standing still case, one per interval. But now let's move towards the source. So if I move towards the source, well, here we go. The observer is now moving towards that source. The source is still emitting. Everything is nice and circular. But you see I skipped two. Now I skipped another two. So every interval now, all of a sudden, I am seeing two waves instead of one, even though this thing is doing exact same emission. So I've increased the frequency if I move towards it, because in each interval I'm seeing two different peaks. And so I would think that this thing has twice the frequency if I'm moving in this way. Okay, so we meet the waves more often, which increases the frequency. If I move away, and I've taken a nice extreme case that I'm moving away at the speed with which the sound is moving, well then cool, I'm always on that same wave. So I think that the frequency is basically zero because there's absolutely nothing happening. I'm always on that same wave, so I just detected the first peak and that's it. Okay, so I then think that the frequency is a lot less. So I can sum that up by this equation down here, where I'm just saying scale the frequency of the source by this factor in their velocities. So I've got v wave plus or minus the velocity with which the observer is moving divided by, the speed, divided by the speed of the wave again. Okay, so all these v's are just the magnitudes, they're the speeds. And so I'm using the plus sign when I'm moving towards, because then you can see that I will get higher frequencies out from my observed frequency, as we discussed. And I'll use the minus sign when I'm moving away from the source, because that will then give me a lower frequency, again, as we discussed in that point. So that's one thing that we can do. We can scale the frequency just by running towards or away from a source. Right. You're probably more familiar with a slightly different version of this effect, which is, let's think about if the source instead is moving. Okay, so again, remember in this video, what we're doing is we're going to take one time step in which we emit stuff, and then we're going to move everything, and then emit, and then move, emit, and then move. All right. So let's now let the source, instead of staying stationary, let's let it move. So here we go, emit, both things move, emit, both things move, emit, everything moves. So the source is constantly moving, in this case, over to the left. And you see each circle, though, is expanding from the point at which it was actually emitted. So they're all centered on their original, on the location of the source when that wave was emitted, which results in the circles getting skewed in this sort of way, as you see in this pattern here. So in the direction that we're moving, things are getting closer and closer, because as the wave wants to move away, the source has moved closer too, and so the next one is closer than it would have been. Conversely, over here, well, that thing's moving away, but the source is moving away, and then it emits, and so those are spreading out. These are getting compressed. So we have a description of that as well. Here is now the observed frequency by maybe someone standing over here on the side where the source is moving towards me, or maybe I'm standing over there and the source is moving away from me. In either case, we can describe it by this formula. It is just the original source frequency times this factor of speeds, where it's the speed of the wave divided by either the sum or the difference of the speed of the wave and the speed with which the source is moving now. And here, remember that what we said is they get closer together, so the wavelength gets shorter, which means the frequency gets higher as we are moving towards. In order to do that, now we have to do it with this plus minus by taking the minus sign, because that's what will make that expression bigger, as the case for when the source is moving towards the observer, and we take the plus sign now when it's moving away. So it's the opposite way as before. So that describes what happens when we're moving faster or when we had the observer moving towards the source. But there's one other interesting point. You can see that the magnitude of this effect, how much you're compressing, depends on the speed of that source. So there's one other interesting question to ask, which is what happens when our source moves faster than the waves? And you can see that now over here, as this source is moving and re-emitting, those things are all piling up, and we're getting a nice sort of V-shaped edge here, leading edge of our progression. So when you look at that, this is what is called the sonic boom. All the waves, all the wave fronts are piling up, and you hear them all at once. So they're all adding together. They're becoming this loud boom because you hear each and every one of them all at once. Okay? And this little sort of V shape at the front, which is now vanished, that little V shape, the sort of angle at which it opens depends on how fast the source is moving, so really how much faster. So this one has this sort of very wide V shape. If we increase the speed a little bit, then what this one will do is go slightly faster, and you will see its V is going to be a bit less steep, a bit less steep, going like this. And you see it's also kind of leading edge thing is happening here, but this superposition along the edges is occurring, and you've got this now less steep V.